So let's model this situation with a bike or the car approaching from the south and a bike approaching from the east in a spreadsheet. So we'll keep track of time, how much between time steps, where the bike is, where the car is, the bike speed, the car speed. The hypotenuse is the distance along the diagonal between them, and how fast the hypotenuse is changing. So according to the diagram we had drawn in the other thing, we've got x is 40 meters and y is -10 because it's south of the intersection. And the bike was moving at 9 meters per second toward the intersection, so its x value was actually decreasing. And the y value of the car was increasing, so we got +4 there. And then what's the length of the hypotenuse? Well, we've got a right triangle, and one leg is the current y position, and the other leg is the current x position. So we can just take the square root of the x position squared plus the y position squared. And so they're 41 meters apart right now along the diagonal. And what else can we say? Well, we need to know where they are a tenth of a second later, or a hundredth or something. It turns out a tenth of a second is fine here. So let's compute delta t, new minus old, and then our calculus prediction equation, current value for x equals previous value for x plus rate of change for x times delta t. And I'm going to put a lock on column B there, because then the same thing happens for y. It's just one column over. Y is one column over from x. dy dt is one column over from dx dt. But the delta t column needs to stay the same, so that's why I had the $sign here. And with those two, I can compute the new hypotenuse length. And then what can I say about how quickly the hypotenuse is changing? Well, I could say it went from 41 point something to 40 point something in 0.1 seconds. So I can just say how much did the hypotenuse change divided by delta t. That's basically a forward difference quotient. So that's what is indicated on the radar of how quickly the hypotenuse is changing. So at this point we could switch to paper and pencil and do all that, and we'll do that in just a minute. But what's fun while we're here in the spreadsheet is to say, okay, that's what happens after a tenth of a second. Or I guess we could say, what if I use a smaller time step? Right now, at a tenth of a second, I had 0.96. At a hundredth of a second, I got 0.97. I could use a thousandth of a second, still 0.97. So I think my time steps are small enough here. Let's go back to 0.1. So I can fill this formula down. I can fill this formula down. It would be nice before I fill down to say, well, what's the new speed going to be? The simplest thing would be to say this car and bike are just using constant speeds, no acceleration is happening. So the new speed is just the old speed. Just easy, nothing to update. And then I can highlight all this and fill down. Notice I didn't highlight the top row there because the top row is just numbers. If I had highlighted both the top row and the second row and filled down, it would have alternated number, formula, and that's not what I wanted to do. The blue highlighting kind of helps me notice if that happens. And then I can fill down dh dt, and I've got the graph already set here. So you can see that the distance decays pretty much linearly, and then they kind of pass each other. I'm not sure which goes first. I'd have to think about that. And then they get farther and farther away from each other. Do they actually hit each other? Well, we can see what's the closest they get. It's let's see if it'll tell us here. It looks like it's about 7. So yeah, distance of about 7 meters. So they're not. It's not a super close pass, but maybe still not comfortable. And we can see the rate of change of the distance between them as they go. Except it's got this little thing at the end. So let's go look at that. And That is doing forward difference to a data point that doesn't exist, so that doesn't make any sense, and we'll just delete it. So that's our graph of the two of them approaching each other and then passing, hopefully safely, only 7 meters apart, and then getting farther away from each other. So now let's go do that on paper.